No formal prerequisites. We don't require that you took 701, for example, or 702 or 707, which are the first two are ML courses. The latter one is a stats course. But as I mentioned, we do assume that you are familiar with core problems in stats and machine learning, although I think you can probably play a bit of catch-up if you're not super familiar with that. Real analysis, calculus, and linear algebra, we assume that you are very comfortable with those. We have some kind of, let's call it refresher material on those subjects at the bottom of the course website. The first several lectures, we're going to draw on that stuff pretty heavily, and then, of course, throughout the rest of the course. But if you're finding that you're kind of rusty with multivariable calculus or something, you can take a look at those notes on the course website. You need to know how to program to be in this course, but we don't really require you to know how to program in a particular language. So the languages we will support as instructors and TAs are the following three: MATLAB, Python, and R. So of us, between all of us, we're comfortable with these languages. Let's put it that way. So you can come and find somebody to get help if you're trying to implement a solution to a problem in one of those languages. R because I'm a statistician, MATLAB because it's kind of, I don't know, it's one of the central tools for people in engineering. And Python, a lot of us like it, and it's a growing language for optimization. If you want to, you can do your homeworks in Julia. No one is stopping you doing so, but we can't necessarily give you help. And, well, maybe one of us can, but I can't give you help in Julia. And I haven't checked with the TAs, but let's just say as of now, we're not supporting Julia. Okay, so these are the languages we're going to support. Data structures and computational complexity. I mean, when I say that a certain algorithm requires O of n time, you should kind of be comfortable with what that means. And really, I think the most important prerequisite is formal mathematical thinking. So being comfortable with rigor. This class is actually fairly mathematical. I think it surprises people, when they sign up for a class in optimization that actually involves quite a bit of math. That's because we're going to take both approaches. We're going to take the approach of how do we prove something converges, and how do we also write down what we expect its convergence rate to be under certain assumptions, and also how do we implement such a thing and make sure that we kind of implement in a way that also takes advantage of structure and so on and so forth. So we do both aspects in this course, and being comfortable with kind of formal mathematical rigor is important. I think that's the most important prerequisite. If you're comfortable with kind of, with that, then I think you can play catch up on the other things that you're a little rusty on or you may have missed. So like I said, come talk to me if you kind of fall short in any one of these categories. But otherwise, I'll assume that everybody is doing, OK. What are you required to do for the semester? You have 5 homeworks, approximately one every 2.5 weeks. So the first one is due, I think, 2 weeks from tomorrow, pretty sure. So it's going to go out maybe today or tomorrow. Then you have 2 weeks to do it. It's a little bit shorter than the usual homework. You have 2 weeks to do it. It'll appear on the course website, like I said. You have 2 little tests. So this is a little different from previous years in which I've taught this course. I used to have a midterm and then a little test at the end. But this year, I'm going to try just 2 little tests. So a little test is just true, false, multiple choice questions, and a bunch of them that are supposed to be kind of about the real fundamental aspects of the material that you've learned. Nothing kind of tangential or really kind of requiring a lot of contortions or creativity to solve. So they shouldn't be very stressful. And I think that you shouldn't even need to study for them. Of course, everyone's different. One halfway through the semester and then one at the end. There's a project option for this course. If you're enrolled in the course for 12 units, then you'll have to do a project. You'll get details about the project as the course goes on. You have 2 milestones basically to meet, and then the project to submit and present at the very end. If you don't want to do the project, then you can sign up for a 9-unit option of the course where you're graded on basically everything else but the project. And many easy quizzes. So after every lecture, there's a quiz that you have to take. It's 8 questions long. It's just true, false, or multiple choice. And this one, I promise, you really don't have to study for. Or you don't have to really, you shouldn't have to worry too much about these quizzes. You can redo the questions as many times as you want until you get them right. And all that we require is that you do the quiz before midnight. Okay, so they're due at midnight the day of the lecture. And there are 8 questions about the lecture that day. So if you came to class, the questions should be pretty straightforward, just to kind of keep the material fresh in your mind. The little tests are really just an extension of that. It's just like taking a bunch of quizzes all at once of this type. Okay? No quiz is due today. We're not going to release a quiz that's due on the introductory material at the start of next lecture, or if I have enough time today, after we kind of make it through the material for today, I'll go through the quiz with you, just so you can kind of see what it's like. We have an hour and 20 minutes, right? Okay. Sorry, I just want to make sure I was pacing myself. Okay. Few more things. Scribing is optional. That just means basically writing up some detailed notes about the lecture. There's a sign-up sheet on the course website, and up to 3 people can sign up to scribe a particular lecture. That means you guys make sure you come to class, take very detailed notes, and then you get together and you 3 or you 2, or just by yourself if you're the only person signed up for that particular lecture, you write a detailed kind of summary of the lecture's contents. Oftentimes there'll be stuff written on these notes that is not in the actual slides. Like maybe I'll give some more detail, or if we have a proof, I'll give kind of a bit more steps or something. And so the scribe notes are nice for putting that all together. These aren't required, but in the case that you are right on the boundary at the end of the semester between like one grade and the other, then that can help bump up your grade to the higher one. So I would encourage everybody to sign up for scribing. And this year we're going to make sure that the scribes are handed in a week after the lecture. In previous years, like scribes from the first week weren't turned in until after the midterm and stuff, and that kind of defeats the purpose. So we're going to be very strict about the scribes this year. You're not graded on them, right? So shouldn't be a huge amount of stress in creating these scribe notes, but if you scribe, you must submit the scribe notes by a week after the day of the lecture. We're going to film the class this year like we've done in previous years. My feelings about filming have been I've been kind of a bit ambivalent about these lecture videos. I think they're very helpful for people to go back and to take a look at the what's been said. If I do something incredibly embarrassing, then you guys can go back and look at that and laugh and put music behind it and put on YouTube or something. But no, but in all honesty, I don't like the lecture videos because I think that they hurt attendance. So I really want people to come to class. I mean, I think that actually coming and listening to somebody give a lecture and then interacting and asking questions, it's second to none in terms of how well you can learn. So the lecture videos are there. I think we'll probably have them up like pretty soon after the class. We have excellent TAs who are going to be managing all that stuff, but I still encourage you guys to come to lecture. Okay, just a couple of things. Auditors, if you want to audit, I'm totally fine with that. I just ask that you don't take up like physical seating room from people who are signed up for the course. And please formally fill out an audit form and have me sign it or have Javier sign it if you track him down rather than just sitting in. It just helps us keep track of numbers. And yeah, I think this class is going to be a decent amount of work, but I think it's also very fun. I think optimization is of course I'm biased, but I think optimization is a pretty cool topic. So yeah, it should be a good semester. Any questions on the administrative side of things before we start? Yeah?
The dates of these little tests like set in stone because some of us might have conference in the middle of the semester to go through.
Mm-hmm.
So let's say fashion first.
Yeah, they are set on the course. They are set on the course website. If you have a hard conflict, then we can certainly accommodate that. I mean, not if you're going on vacation, but if you have a conference or something, yes. I should also have mentioned this. Thank you for reminding me. I should put on the lecture notes too. I think it's in the syllabus. Okay, so the detailed syllabus is on the course website. Make sure you read that because you'll have all the details that I missed here in the syllabus. But our late policy is an important one. So if you have a conference deadline or you have some amazing clash of like you have a midterm and 2 other homeworks and whatever all due this day and our homework's due that day, then we will allow you to have an extension for the homework, but you have to give us 5 days notice. Okay, conference can't be coming up and then all of a sudden the day before you say, I can't turn the homework in. 5 days notice. If he gets 5 days notice about some conflict like a conference deadline or you're going to travel to a conference or you have like a lot of stuff in your graduate studies coming in all at the same time, that's fine. Just give us 5 days notice. If you have a real emergency like some family problem or something, then you don't need to give us notice. That's the nature of emergencies. You can't foresee them. So of course that's okay, but for the type of thing that's not an emergency, like a conference deadline, et cetera, you need to give us 5 days notice. Okay? Otherwise, there's no late work that we accept. Any other questions? Okay, so we did that in a little over 15 minutes. That was pretty good. So let's get to some of the motivating material for the semester. Optimization problems, I think I don't really have to convince you of this. Hopefully you all agree. They're pretty ubiquitous in statistics and machine learning, and also in many other disciplines. But these are my fields of expertise, so of course that's like I said, we'll be talking mostly about these 2 fields. They underlie almost everything we do, I claim. So in many other courses, like let's say in 701 or 702 or 707 or 715, if you're an ML student, you'll learn how to take some kind of idea, like I have data and I want to get this out, this particular function out, or I want to study this relationship, or you have some kind of, let's say, conceptual goal. You learn how to translate that into a particular optimization problem. Okay? In this class, you're actually going to study the details of this guy. We're not going to talk about the translation so much. I have this goal. How do I formulate an optimization problem? That'll, of course, be part of what we do. But what we study more is the actual problem itself and in all the glory detail. How do we solve that problem? How do we derive conditions for optimality in this problem? How do we understand the nature of the solution, et cetera, et cetera. So I thought it would be helpful. Let's just start off by listing some examples of kind of tasks that we do in statistics or machine learning, or your field, if those aren't your fields, and what the corresponding optimization problem is. This light is... OK. All right. So yeah, any examples? Just yell them out or raise your hand. Doesn't matter. Regression, right. So what's an example of the optimization problem? I mean, regression is kind of general. So what in particular do we do when we want to fit a regression model? Right. So least squares is probably the most standard, right? So we minimize the sum of squared errors of some response or target to some predictors or covariates or something, where we measure goodness of fit by squared error loss. Okay, that's least squares. Okay, let's just even stick on regression. What other types of regression are there? Optimization problems and least squares. Sure, yeah. I mean, so this is now getting to regularized regression or penalized regression. So there's the lasso, which is usually formulated as minimizing the least squares loss subject to a constraint on the L1 norm of the coefficient vector. Okay, so this one we usually formulate as minimize overall, let's say, weight vectors or coefficient vectors beta, the sum of squared errors of some target variable y to some predictor variables xi, transpose the coefficient vector. And this one is usually, set up similarly, but where we place a constraint on the so I'm writing out all of the norms here, just because maybe people aren't, maybe this is another parameter. It's like a tuning parameter, t. So we minimize least squares loss subject to some L1 norm constraint. There's also least absolute deviations, LAD regression. It's another example where we just replace the squares here by absolute values. So statistically, or from the point of view of what we're trying to do, using the least absolute deviation problem, solving that problem where we actually have these being absolute values rather than squares, that's usually called a robust version of regression. Okay, that's because we're placing less emphasis on outliers. Right? If a point yi is very far away from the linear trend we're trying to fit, we're placing less emphasis on moving the line to kind of catch that. So that's the goal. How do we do it optimization-wise? We use absolute value rather than square. That actually makes the problem harder to solve, though. This guy's non-smooth. This guy was smooth. Okay, so it has some implications. What other types of problems? I mean, there's so many. Sorry? Okay, so we're kind of moving, right, we're moving to classification. So in classification, I'll write down first logistic regression, which is easier than what was just said. So in logistic regression, yi is binary. It's 0 or 1. So now we're, instead of trying to predict something that's continuous, like a continuous variable, we're trying to predict just a label like 1. And we can formulate it in a similar way, okay, with what we call logistic loss. There's also the 0, 1, using 0, 1 loss, which is, basically, we're going to say if we predicted the class to be 1 and the class was 1, we get no loss. If we predicted the class to be 0 and the class was 0, we get no loss. Otherwise, we incur a loss. Okay, that's actually something that is of interest, but it's a very hard problem because it's non-convex. So in some sense, it's very hard to solve. As we're going to kind of harp on that point a lot. The first word of the title was convex optimization. That doesn't mean that we're not interested in non-convex problems. It just means we're going to emphasize that there's a big difference between the two. Other examples?
Hinge loss.
Yeah, so we can do hinge loss. This kind of relates to support vector machines. A staple of machine learning. Other examples. Doesn't have to just be in statistics and machine learning. I always feel like I learn a couple new problems in this lecture because people tell me that there's problems in their field that I haven't heard of. So what about people outside of like robotics or ECE or any other disciplines? I'm sure you guys have optimization problems. I didn't understand any of that, so something simpler.
Basic optimization problem, discrete optimization problem, like the traffic salesman problem.
Okay, yeah, sure. That sounds like a classic CS problem. So the traveling salesman problem, other kind of planning problems or discrete optimization problems. I think at the very end of the semester, we'll talk about integer programming. So we'll hit on some problems that are related to those. Anything else? So I'll just keep listing a few. So this is one that all my statistics friends will be very familiar with, maximum likelihood. Maximum likelihood, well, you can tell by the title, is an optimization problem. Maximize the likelihood. And that underlies like a huge amount of what we do in statistics. Of course, not every problem is a maximum likelihood problem, but these logistic regression, least squares regression, least absolute deviations, these are all special cases of maximum likelihood estimation. Okay, so, and there's a big emphasis when you study likelihood estimation in having concave likelihoods. So you want to maximize a concave function. It's equivalent to minimizing a convex function, right? So certainly, of course, convexity, concavity plays a big role there. So we could go on and on. Literally, I think we could fill pages with optimization problems. I think it's kind of fun sometimes just to point out that optimization is not everything. And what are some examples of tasks that you may do in statistics and machine learning or in other fields that aren't optimization problems per se, but that are still kind of important? These are more procedures rather than optimization problems. Or at least, I mean, okay, there's kind of a gray area here. What I'm trying to say is the final answer is not itself optimal with respect to any one criterion. Yeah, sure. I guess, I mean, it's true. Anytime that we do, right, so hypothesis testing or computing p-values. Those aren't always formulated. In fact, rarely formulated as kind of a solution to an optimization problem. So this is optimization. These are non-optimization topics. Even if we stick along the lines of, some of these prediction problems, right? Like fitting a function, either a linear function or a sparse linear function or a linear function in the logit space or something. There are lots of things that we do in these fields that aren't necessarily themselves a solution to a single optimization problem. So for example, boosting is one very popular method that, okay, you may argue has connections to optimization, but the output of a gradient boosting machine or something, which we'll talk about in like 4 lectures or something, is not itself optimal with respect to one criterion. At least that's not how you always view it. Same is true with random forests, right? So a lot of these ensemble methods, they're very powerful. We talk about them all the time, but they're not necessarily the solutions to optimization problems. Things like cross-validation or the bootstrap. So if I want to estimate how well my method is doing out of sample, right? If I were to take this to new data, what is its test error going to be? Or what is its prediction error going to be? I don't formulate typically an optimization problem and then solve that, and the solution of that is my estimate for the test error. That's more rare. More common, I do something like cross-validation or the bootstrap. These are just procedures. Okay, these aren't necessarily things that, the cross-validation estimate of prediction error isn't itself optimal with respect to some criterion. It's just the result of splitting it up into, like, let's say 10 parts, training on 9 parts, and testing on the 10th. Okay, so there's actually, if you dig deep, there's quite a bit of things we do that we're actually pretty comfortable with that aren't optimization problems. They're outside of the scope of what we can say based on the tools in this course, mostly. I mean, we can still talk a bit about something like boosting, for example. Random forest, in some sense, you can discuss connections to optimization, but they're not rooted in optimization. And this is kind of maybe a bit less clear, but I claim that actually a lot of the stuff we write down in this category is less well understood in some sense formally than the stuff that we write down in this category. It's much harder to understand cross-validation than it is to understand some kind of particular output of an optimization problem in general. Okay, when things are posed as procedures, then to understand them, we must require that specific procedure. We have to kind of think about, if we want to talk about theory, we have to think about studying the steps of that procedure in sequence and thinking about if we put in this type of data, what does it do to this data and what's the output. When we want to understand the output to an optimization problem like the lasso or SVMs or something, then we actually, because it's the output to a convex optimization problem in particular, we have things that are called optimality conditions that allow us to talk about properties of the solution that are independent of the algorithm that you use to get it. Okay, that's the power of studying optimization in general, is that you can kind of make you can come to conclusions about the nature of the solution without needing to talk about the particular way you got the solution. Whereas these things are tied to the procedure. They're defined by a procedure, right? So to study cross-validation, you really have to study that particular algorithm. Okay, so it's important just to maybe keep that distinction in mind. Of course, this class, like I said, is going to be focused on the optimization problems, and so we're going to be talking about them from now on. All right, so I kind of already gave you some answers to this, but just to for completeness, you could pose the question. Presumably, a lot of people know how to solve the lasso. It's not like this semester we're going to come up with an algorithm nobody's ever seen. It's probably pretty unlikely, and there are a lot of algorithms for solving the lasso that are quite good. So why do we care, right? Why don't we just call someone's Fortran code or MATLAB code or Python code, whatever? Well, there's 2 reasons. The first is that, and I'm going to try to give you examples of both these reasons in class today. The first is that different algorithms can perform better or worse depending on the situation. And by situation, I mean the data. Okay, so it could even be somehow like a similar setting, but the data instance, the particular type of data you're expecting may be kind of different in one case or another. Okay, so we could be solving the lasso in this case. We could be solving the lasso in this case. And they could be different enough that actually we may want to use different algorithms. So understanding what algorithms are out there and how we expect those algorithms to perform is very important. Okay, because we may end up, they actually can make quite a big difference. So I'll give you an example of that just in a little bit. And the second reason was one I already kind of touched on, which is that studying this problem can often give you a deeper understanding of kind of the nature of the solution to your problem. So if you're a statistician or a machine learning researcher, it's maybe the statistical properties of your estimate. Okay, but if you're not in these fields, it still is, you can understand properties of the solution by understanding the kind of gory details of the optimization problem itself. A third reason, which is I think it's worth mentioning, I think these are the real two reasons. Third reason, which is that it's a very current field. I think it's actually quite fun to study optimization because it moves so fast. So if you look at the NIPS workshops on optimization, every year they change. You know, a couple years ago, it was about non-convex optimization. And I felt kind of a bit shy that semester to bring that up because I was talking about convex optimization for the whole semester. And meanwhile, the biggest machine learning conference in the world, their optimization workshop is all about non-convex methods. But that was because that year, there was a huge amount of development and provable convergence for non-convex problems. Okay, it's like just an explosion of research happened that year. The year following that, it was all about revisiting stochastic optimization. They'd made all these advances in variants of stochastic gradient descent that are much faster than what we typically think of. And it changed every year. So I think it's actually very exciting because it means that there's still a lot of room for progress. You know, you're not studying a very old field where, you know, essentially you have to have a major breakthrough in order to write a paper. That's not at all the case with optimization, especially at the intersection of statistics and machine learning. So let me pause for questions before we get to our examples. Okay, usually about now, usually about now I would actually give us like a 5-minute break, but I think I'm just going to power through and try to end early. From now on, when we have kind of content for the full 80 minutes, I'll try to do 40 minutes, a break, and then 40 minutes. But I think maybe we can just power through and I'll go home a bit early. So here's a few examples that I wanted to mention. They surround, all the examples surround kind of the concept of total variation denoising, or the fuse lasso. It's two names for the same thing. And you'll have actually a bit of this on your first homework. You're going to solve a 2D total variation denoising problem of this type. And I'm not 100% certain, but I'm thinking about later in the semester doing a case study on TV problems because I'm interested in them. I thought we always try to find, you know, 1 or 2 topics each year to do a case study on. Like we'll tell you all the algorithms we can think of for solving a particular problem and discuss their properties and stuff. And so maybe we'll do TV denoising this year. So it's a pretty, this platform covers lots of different problems. Here I'm showing you image denoising, which is a particular case of the fuse lasso or total variation denoising, where we have data that's arranged into a 2D grid. So this data, y1 through yn, that's like taking this picture and unraveling it into a vector. So just think about unraveling it, say, like row by row or something, or column by column, doesn't really matter. And let's suppose we associated a color scale with the value of y. So just for simplicity, suppose y was between, the values of y were between 0 and 10. And here, or I guess here I have 3 and 7, sorry, and here's the color scale that I associated with it. Okay, so 3 is down here, it's green, and 7 is red. This is just for a visualization. And let's suppose that we think that some image that we're trying to kind of recover is actually piecewise constant. It's blocky. So that means that the values of y don't really change much across the image. Okay, only in a few kind of on a few edge boundaries do they change. So let's suppose that's the image that we're trying to recover. But because I wanted to compress this image, or maybe because I'm actually observing it, like this is an MRI scan, it's not something that I can see directly, or whatever other reason, let's suppose that what I observe is a noisy version of the image. Okay, so this is the data I see. This is actually y. I meant to say this was, let's say, the mean of y, not y itself. This is y. Okay, so it's no longer piecewise constant. And what we want to do is to recover some kind of piecewise constant structure. Now, there's a lot of stuff you could do if you took a class on image denoising. I'm sure that there are experts in image denoising that would tell you that what we're doing is maybe kind of simple, but at least it's an optimization problem that we can set up and solve. It's going to give us a pretty nice answer. So what we're going to do is we're going to solve for some parameters theta. Okay, that's going to be our parameters, optimization parameters. And we're going to have one parameter theta I per data entry yi. So actually, theta is also going to be an image that's unraveled into a vector. And if we want to, we could put it back into an image just to display it visually. And theta is going to be optimal with respect to the following criterion, the one I wrote up there. So there's two terms. The first is just least squares loss between the data at pixel I and parameter theta I. Okay, so this is just saying that we want our fitted values, theta I, to be close to the data. Right? That, otherwise, there's kind of no data quality term. Of course, we want close to data. Okay, so this value lambda here is actually something that we choose as a user. It controls the weight of these two terms. So something we often call a tuning parameter or a hyperparameter. But suppose we fix that at something large, like I think I used 25 or something in the examples here. What is the penalty itself? So the penalty itself, it goes through all the entries of theta, I and j, that are adjacent. In other words, I've written down here that the pair ij belongs to some set E. E is a set of edges. So imagine actually what I did is I took every pair of pixels in this grid, and I joined them by an edge if they were horizontally or vertically adjacent. That's the set E. It gives you all the adjacencies, so things that are next to each other, either horizontally or vertically in this image. And here I'm penalizing the absolute difference between all adjacent entries of theta. Okay, so it's saying that I think if I were any one pixel and I were to move up or down, or left or right, I think that the pixel values that are neighboring should be similar with respect to their, the absolute value. Okay, so if you were to have seen the lasso in, say, 701 or other problems, or you were to do L1 optimization and other courses or whatever in your research, you might recognize that actually what the effect of that term there is going to be is to induce sparsity in the differences. So actually, when we solve this problem, if we make this parameter lambda large enough, we're going to get that theta I and theta j are exactly equal for many i's and j's. Okay, so we're going to get just one consistent color between adjacent pixels. And what this is doing is that it's actually adaptively setting a lot of adjacent pixels to the same value in such a way that we get a blocky image, but in a way that simultaneously balances the goodness of fit to the data. Okay, so it's actually quite a sophisticated procedure, but optimization-wise, it's pretty simple. Just two terms, and there they are. So this is the output of running, of solving this optimization problem on this data instance. It's right here on the right. Solution, I think I took lambda equals 25. I just picked something that was relatively high for visual purposes, but I didn't try to optimize, test error or anything like that, just an example. Okay, and as I make lambda larger and larger, what you're going to see is that this image becomes more and more piecewise constant. So the colors are going to get closer and closer together. Maybe we might start merging actually these two blocks, which have slightly different colors. This is like a blue, it's like a purple. That might become all one color. And what happens if we take lambda to be infinite? What do you guys think the solution is going to be in that case? All the same color, and that color is going to be what? I mean, not that you can name the exact color, but what is its value going to correspond to? The mean of y, right? So basically, this penalty term is going to force us to just choose one value for all the components of theta. And then subject to that, what's the smallest we can make the first term? It's smallest if we set all the thetas equal to the mean. Right? So that's going to be the solution if we take lambda to be too large. And what happens if lambda is basically 0? Like really close to 0? We'll just get the same image pretty much, right? And if it's 0, we get the same image exactly. So that's the full set of solutions. Somewhere in the middle, we get something nice like this. OK, so that's our problem. How did I get that solution? How did I get this? So that's going to be the point of this course. We're going to talk about how you actually, well, not the only point, but one of the main points of this course. How do we get that solution? So I actually got that using an ADMM algorithm, something we're going to learn towards the end of the course. We're going to spend 2 lectures on it because I think that ADMM has become so important. It stands for the alternating direction method of multipliers. You guys may have seen it. If you look through the optimization literature, there's quite a bit of work on that nowadays. And it wasn't just any ADMM algorithm. It was actually a specialized one that I set up that I knew would work particularly well for this problem. And the reason I knew it would work well is because, well, I've taught this course a number of years in a row, so I can kind of understand at least how I expect ADMM to work in certain situations. And I think that you guys will be able to come to the same conclusion after having taken the course. So it was a specialized ADMM algorithm that had kind of components that I thought I knew would work well. And I only ran it for 20 iterations. Okay, this image was like I think it was like 300 by 200 pixels or something, or 300 by 150 pixels. So it's a decent sized problem. But this algorithm only took 20 iterations. And each iteration was only linear time. It was very fast. Okay, so this whole thing was like a fraction of a second to compute this image. We won't get to that algorithm until the very end, or maybe close to the end. What's another option is proximal gradient descent. So this one we're going to actually get to fairly soon. And this plus duality would give you the ability to implement this algorithm. So you should be able to kind of implement this, or at least understand this algorithm fairly soon, early on in the course. And that was what it gave me after 1,000 iterations. Unfortunately, the projector is not great. But you can take a look at the slides online, or maybe you can just try to kind of look back and forth. You can see actually the one from proximal gradient is much less piecewise constant. It doesn't have the right kind of fusion, right? It doesn't fuse adjacent pixels together to the exact value. It has kind of these like artificial rings and stuff. So even after I have like 1, 2, 3, 4, 5, 6, 7, 8 colors and more, where I should only have something like 3. And this is after 1,000 iterations of this algorithm. If I ran it for 10,000 iterations, it would get kind of close to this solution. Every iteration here is also linear, okay, but it's converging a lot slower. So not the right tool for the job, so to speak. Lastly, I ran coordinate descent. Coordinate descent is like a super popular method, like ADMM. We're going to spend, I think, at least a lecture on that towards the end of the course. I ran it for 10,000 iterations. Each iteration here, it's really called a cycle. Is it also linear? But it's not even close to converging for this example. And in fact, this picture was so bad that what I did was that I actually took the proximal gradient solution after some number of iterations and plugged that into coordinate descent. Because coordinate descent, starting from kind of a naive estimate, it looked much worse. It didn't even look like this. Okay, so it's absolutely not the right tool for the job. So these are orders of magnitude difference in terms of how costly they are to run. And there's also a big difference in terms of the quality of the solution. The last two were run from the dual problem. So when we learn proximal gradient and coordinate descent, you may come back to this lecture and think, that doesn't make any sense. How do I run it on this criterion? Well, it's because I ran it on the dual. And that'll be also something you're familiar with doing after the course, taking the dual of the problem and then thinking about how to apply algorithms to that instead of to the original problem. So what's the right message here? Am I trying to convey that ADMM is just like way better than proximal gradient and coordinate descent? No. In fact, ADMM is much worse than coordinate descent in some situations. In other situations, proximal gradient is very reasonable. So what I'm trying to convey is that different algorithms will work better or worse in different situations. Okay, so understanding the full suite of possibilities and also the properties of the algorithm and when we can expect them to work well and not work well is very important for choosing an algorithm before you deploy kind of software or you run. If this image was, let's say, 20,000 by 30,000 pixels, or instead of an image, if it was a 3D MRI scan and it was 100 by 100 by 100, you wouldn't want to have to wait 2 million iterations for coordinate descent and find that it gave you something like this. Okay, so these kind of decisions matter. So just for future reference, we may come back to this example, though I'm not sure we will. But for future reference, after you learn these methods, you might come back and realize that the coordinate descent was slow in this case because what we call the active set in coordinate descent was very large. And it had kind of, because we were applying coordinate descent on the dual problem, it was kind of the wrong setup. So the active set was just too large for coordinate descent to converge. And that'll make more sense once we learn coordinate descent. Proximal gradient was slow because of conditioning. So the condition number of the criterion is very, very poor here. Proximal gradient is a first-order method. As we'll learn, first-order methods are very affected by condition numbers. So it's kind of how curved the criterion is around its minimum. And that made proximal gradient very slow to converge. Specialized ADMM was faster because the particular subproblems that I chose when I set up the algorithm they had a lot of structure. Okay, and we'll talk about that when we talk about ADMM later. Okay, but that was just kind of like a high-level diagnosis. All right. When I already asked this. What time does this course finish? I can't remember. 2:50. Okay, good. So we'll definitely finish early. I was worried. I thought it was 2:20. Any questions about that? Yeah.
Here you're learning the theta for a given lambda. You're not doing the problem of learning what lambda
Correct. So just to kind of put it in context here, let's talk about denoising. TV denoising, or the fused lasso, is a particular optimization problem that we just saw a bit about. And then how to choose lambda, you could actually use cross-validation for that. Well, okay, it's a bit tricky in the image. You could use cross-validation for it. It would be kind of a creative use of cross-validation. What I would do is I would leave out every other pixel. I would take every other pixel in the image in like a checkerboard fashion. I would pretend like I didn't observe that. And then I would try to fit an estimate on the pixels that I did observe over a bunch of lambdas and choose the one that had the best kind of out-of-sample error. But that, I mean, that's kind of a non-standard use of cross-validation. But that's a way to choose lambda, for example. Good question. Yeah.
So, about that, so how does the cross-validation work? Because we don't have the true.
Right. So instead of minimizing, let's say the distance to some true image, I could just try to minimize prediction error, which under many models would be kind of like the same goal. So I'm just saying what you could do is, take your image and let's suppose I'm going to leave out all these pixels, etc. All the ones that have an X. Take those, form a smaller image out of them, and form a smaller image out of, etc. So I just would kind of rearrange them so that these two are adjacent. I mean, I'm talking about something pretty hacky here because people don't really do cross-validation for image denoising, but this is something you could do. Solve the total variation denoising or fused lasso problem here for a bunch of different lambdas, and then for each of those values of lambda, measure the error to the left outwise. Okay, and that would be a way to try to choose lambda. Take the lambda that gives you the smallest out-of-sample error. Okay? Other questions? Good questions. Okay, so that was our example about different algorithms working better or worse in different situations. I'll give you another example about things you can learn from the optimization problem. And this is actually an example taken from the thesis proposal of one of your TAs. In my opinion, has a pretty cool thesis proposal, but I'm, again, biased because I'm the advisor. But here's an example of how we might take something from optimization and then kind of learn something that is beyond just the solution, right? Draw some kind of statistical insight about the properties of the solution. So now we're going to go back to this total variation denoising problem. And instead of looking at the 2D problem, we're going to look at a 1D problem. So it's a lot simpler in some respects. Now we have data, again, y1 through yn. But instead of being like an unraveled image, it's just data that lies along a line. And I actually think that the mean of y, let's say, is itself piecewise constant. And by piecewise constant, again, it's a more simple notion. It just means along that line. Rather than a 2D plane, it means along that line. And so we're going to try to find a parameter vector theta to estimate the mean of y based on solving a problem in which we have two terms that are very similar to what we had before. Right? Here we had two terms that, like, this was called usually like the loss term, so the loss to the data, and this is the penalty term to give some kind of structure to the solution. And it's analogous here, except for the only difference is the penalty term penalizes the differences between theta I and theta I plus 1, because those two are the only two that are adjacent in 1D. Right? I don't have kind of different directions to look at. So here's an example, right? So let's suppose they're kind of light gray points. These are my y points. I'm plotting them versus the index, 1 through 100. I think probably that the mean is constant here and the mean is constant here. It's kind of obvious visually, but this is an algorithm to do this kind of stuff for us automatically. And I've plotted the solution to this problem at different values of lambda. So when lambda is very high, we just get back the mean of the y's as our estimate, right? That's all the thetas are equal to y bar, the mean of the y's. As lambda is made smaller, then we kind of make more breaks we estimate a piecewise constant function with more pieces. When lambda is 0.62, we get exactly two pieces to our solution, one here and one here. That actually looks quite good. All right, so of course, a pretty easy problem. I picked 2. And then when lambda is even smaller, you can see actually it chose to make another piece here. It broke off this into 3 pieces. That was it was best in terms of balancing those 2 terms in the criterion. Okay, so that's called it's called 1D total variation denoising, or the 1D fused lasso, rather than 2D. And what we call these things here are change points in the solution. So this is a change point, right, because the mean changed. This is another change point. So for lambda equals like 0.41, I have 2 change points, 3 pieces. A change point here and a change point here. Okay, so now we may ask ourselves a statistical question, which is, how significant are these change points? Right? It looks like I said obvious visually that actually this one's important and this one's not. Right? This one we think is probably spurious. Of course, as I make lambda smaller, it's just going to keep making more and more change points. That's the nature of the optimization problem. If I made lambda to be 0.04, I'd get lots of change points. But which of them are significant? Which of them actually matter? So this is something that you can only answer, it turns out, in this question, so to speak, if you understood the optimization kind of properties that are associated with the fused lasso. So let me take you through a little bit of a detour. And we're going to talk about statistics a little bit, but you'll have to humor me. I am a statistician. And I think also it kind of helps bring the point home. So let's take a look at the solution at lambda equals 0.41. Okay, that was the one that, let's suppose I want to take this third picture and ask which one is significant. Is that significant? Is that significant? Are neither of them significant? So what I've done is I've actually focused on this first change point. And now there are 2 regions to consider. I called it region A and region B. Those are the regions that have been estimated by the solution to have a constant mean. Right? It's constant here, it's a little bit higher, and it's constant there, it's a little bit lower. So I could ask, is this difference in mean actually significant given the data in these 2 regions? Now, what you would do classically, if you took Larry's 705 course or you took other statistics courses, then you would learn that what you could do is take the average of the points in A and subtract the average of the points in B and compare that to a null distribution in which you actually had averages from something and averages from something else, and those 2 had the same mean. Okay, so I could ask myself the question, let's look at the observed difference in the averages between these points and these points, and compare that to a setting in which I had just points from A and points from B with the same mean. It's called the null distribution, where nothing's happening that's different, and I take averages anyways and look at their difference. So if I compare that to my reference distribution, and it looks like actually this difference in averages is actually quite high compared to what I expect under the null, then I would say, yeah, actually this difference is real. It's real. So if you do that here, actually it fails miserably. You almost always find that whatever you find is significant. Why is that the case? Justin can't answer. It's a bit subtle. What do we know about this point? This actually was location, I think, 11 in this example. What do I know about that point? Was that just some point that was chosen arbitrarily? Yeah.
So the optimization we are doing, it breaks the piece where the averages differ a lot. So, I mean, that's why there is a break there, so the statistical testing is real.
Right. So the optimization problem itself is trying to find locations where the differences in mean are large. Because that actually, if it could put breaks at such locations, it would make this term small, right? Because it wouldn't have to kind of incur like points in one group where the mean was quite different, and I tried to fit a single parameter to it. So it's actually trying to, it's seeking to find places where the mean difference is large and put change points there. That's the point of the optimization problem. So of course this is going to look like it's pretty high. That's because I chose 11 precisely because it was kind of high for the optimization problem. Okay, I mean, it's like another way of saying it is that let's suppose I had data from just one mean. So it's just completely flat mean from 1 to 100, and I observed change points. I observed data all around that mean. And I ran the algorithm until I got one breakpoint. Now that one breakpoint is going to be the point at which the averages on the left and right-hand sides were as different as possible. That's kind of the nature of the solution. So if I compared that to a case in which the averages were the same, of course it's going to look good because it was kind of like the best among many choices that we could have made at that first step to break the two means up. Okay, so in other words, we've cherry-picked location 11 because it happened to look good from the perspective of the data. So of course it's going to look too significant. Yeah? Yeah, it's a good question. Not exactly lambda itself, but kind of things that relate to lambda. So that's what I'm kind of going to get at here, is instead of just simulating data, here's what we want to do. Instead of simulating data in which the mean was the same and the mean was the same, and then we look at averages, one to the left of location 11 to the right of location 11, we actually want to simulate different data. We want to simulate data in which the mean was all the same here, but after we ran the fused lasso, we got location 11 coming out as a breakpoint. Because that's precisely what we're looking at, right? If it happened to be that we ran the fused lasso, we got location 11 out, and these two were actually happen to be the same mean, we want to be testing against those cases. Because for us, on our data instance, we actually got location 11 popping out at us as one of the change points. So in other words, if we didn't care about computation, and we just wanted to simulate as much as we could simulate a bunch of data sets in which the mean was just the same here. We could run the fused lasso, and then we could only keep the instances at which there was a change point that came out at location 11. And in fact, we really actually want change points coming out at location 11 and 50. We want to kind of recreate our setting exactly. We had data that just came from, let's say constant here and constant here. We ran the fused lasso with lambda equals 0.41, the same lambda I used before, and we got a change point here and a change point here, just like we saw in our instance. Okay, and we want to collect all those instances, and we want to take averages between the data in region A and B, and then compare those differences to the differences we saw. If we could do that, that would kind of be the right thing to compare against. It's putting the comparisons on equal footing, right? Because in each one of these instances, this was our actual observed data. I simulated this. We also chose location 11 as a breakpoint and location 50, so kind of everything's on equal terms for the comparison. Now, it took me 1,222 simulations just to find one. I just did like accept, reject. It means I just kept simulating until I found one in which the breakpoints were again 11 and 50. It took me about 1,200 times to get that for one reference point. Now suppose I want like thousands of reference points, so I can build what's called a distribution and figure out how big is this absolute difference compared to what I see by chance. That would just be way too costly. And this is actually kind of a small problem, right? It's just 100 points. So it turns out what you can do is if you understood the nature of these change points, if you understood the solution to that optimization problem, then you could answer this question without simulating. You could say, the properties of the data that make it so that the solution has a change point at 11 and 50 are as such. And you can actually answer this question without having to simulate. And that only comes from kind of a precise understanding of what it means for something to be a solution to the fused lasso problem. You wouldn't know how to do that without understanding precisely what it means to be a solution to the fused lasso problem, and what it means to have a change point here and here, let's say at a particular value of lambda. And there's something we'll learn halfway through the course called the KKT conditions, the Karush-Tucker conditions, that characterize optimality. So if you study those, then it turns out you can devise a way to compute what we call p-values, significance tests, for change points that don't require simulation at all. Okay, and that's just an example of like where optimization comes in handy outside of computing solutions. It can tell you something about the nature of your statistical problem in the first place. So there's a paper online you can take a look at that does this. Shameless plug. But questions about that? Okay, so I try to change these examples each year, but there are lots of examples in which you learn something about the optimization problem, tells you something about the solution that's kind of beyond just computing the solution. It gives you some insights into the properties of the solution. And of course, like the details of this example aren't important. They're just supposed to be motivation. So if something didn't make sense, then don't worry about it. But of course, you can come ask me questions about it. So let's kind of get towards the last couple things I wanted to talk about. A really central concept in this course is convexity. Historically, linear programs with a focus on optimization. Javier is not here today, so Javier is more senior and more experienced than me, so if he was here, he could correct some of my history, but now I'm at the liberty to kind of make things up. Linear programs with a focus on optimization. So people traditionally studied linear programs intensely and they came up with very pretty solutions to linear programs. And there used to be entire courses taught about linear programming itself. Okay, that still kind of exists in operations research. I think actually in Tepper, which is where Javier sits as a faculty member, they have courses on linear programming. And it was thought to be that the distinction between linear programs and nonlinear programs was the important distinction. So you had linear programs, which you could all solve really nicely, and then nonlinear programs, and those were a lot harder. But it was kind of discovered at some point that some nonlinear programs were actually pretty tractable. Right? We could get away with solving a bunch of nonlinear programs in a way that was efficient. Like, for example, this one. It's not a linear program. You'll see a precise definition of linear programming in a couple lectures, but it's not a linear program. We can still solve it efficiently. But other nonlinear programs were like virtually impossible. Some of them were just really, really hard to solve. And it was recognized that the right distinction is not between linear and nonlinear, but convex and non-convex problems. So now I think it's pretty widely accepted. I don't think anybody would disagree with this, at least not at kind of a fundamental level, that convex problems and non-convex problems are very different animals. Convex problems, we can talk about generic algorithms to solve convex problems. Some may work better or worse depending on the situation, but they all have provable conversions. They all will work eventually if you run them long enough. And a suite of tools called KKT optimality conditions and duality that we can put on top of convex problems to understand properties of those solutions. Like to characterize optimality. What conditions do you have to meet before something becomes optimal for a particular problem? Non-convex problems are kind of more hit and miss in the sense that you can give me a non-convex problem that maybe I can tell you how to solve, but then you can change that problem ever so slightly and it would become very hard to solve it. Or at least it might require a whole new algorithm that I maybe don't see. So it's an important distinction, and we'll kind of throughout the semester talk about non-convex problems, but not nearly as intensely. 2 supplementary textbooks for the course. The lectures are self-contained, so you don't need to get any other references, but there are some you can rely on if you find them helpful. I think this is a really great book, the Boyd and Vandenberg book, Convex Optimization. It's freely available online. And some of the examples and stuff that are not to do with statistics and machine learning I'll draw from this book because it's kind of more a pure optimization treatment. I also really like this book. It's a book by Rockefeller. It's called Convex Analysis. These 2 books could not be more different. So this one is like a very, it's very long. It's like 400 plus pages. And it, I think, has like a lot of examples, and it's kind of gentle. This one is very short, and it's like a 150-page math book. So everything is just really kind of terse. But I think it also has a lot. It has a lot in there. And so if you don't find something in Boyd and Vandenberg, and you're kind of willing to, to give it a shot, Rockefeller actually does have a lot of really important stuff. And of course, you can come ask us for references on anything in particular that you're curious about. And at the end of every lecture, I also put I list references for more material on that particular subject, so you can also look at those. So let's finish off by just discussing, a couple more things. Convex sets and functions. What are those? Convex optimization, and then a key property of convex optimization, and then we'll quit. So a convex set, this is probably something that a lot of you guys have seen before. We'll have an entire lecture on Wednesday on convex sets and functions. So we'll just kind of dive into that. But here's just the definitions. A convex set, C, is a set in which the following property holds. If I give you any 2 elements of that set, and I take the line segment that lies between those 2 elements, join those 2 elements, then that entire line segment is contained in the set. Okay, so if I have a convex set, and I take any 2 points x and y, and any intermediate point, okay, x and y. This intermediate point is of the form tx plus 1 minus ty. It interpolates x and y. T here goes between 0 and 1. Right? When t is 1, we get x. When t is 0, we get y. Somewhere in the middle, we get this somewhere on this line. A convex set has the property that this whole line segment lies in the set. It's a key property of a convex set. Okay, so that's just what this is saying. Tx plus 1 minus ty is in C for all t between 0 and 1. So a non-convex set is like this bean shape up here. Right? Here I have x and y, but the line segment actually lies outside of the set for some values of t. So it's not a convex set. Okay, convex set. Convex function is one in which, so we're going to talk about functions this year that are real valued, so from Rn to R. Okay, and what is a convex function? It's one in which it has a convex domain. So the domain of a function is just the set of all values for which the function is defined and finite. So for example, log of x has a domain that's the positive reals. Right, so the domain of log is, we write that usually as R++. It's the set of all x that are real valued in positive. That's the domain of log, because log is not defined at 0 or for negative numbers. So your function, right, that lives on Rn, n-dimensional Euclidean space, it could also have a domain that's not all of Rn. So for a convex function, we require the domain, which is a set, right, in Rn, to itself be convex. So it must satisfy that definition up there. And it must have the following property. It must be the case that the function evaluated at any 2 points lies below the line segment joining those 2 points. Okay, the graph of the function. So mathematically, if we take our function and we evaluate it at tx plus 1 minus ty, that must lie below t times f of x plus 1 minus t times f of y for all t between 0 and 1. So there's a picture. Right? This is the point x comma f of x. If, for example, my function is defined on R, this is y comma f of y. And this is what it looks like to evaluate f at any point in between x and y. And a convex function must have the property that the graph of the function lies below the line segment, joining x comma f of x to y comma f of y. Okay? So that's the definition of a convex function. As we're going to see next time, actually, these two definitions are very, very closely aligned. So if all you knew was convex sets, I could teach you all about convex functions. They're not really separate cases. That's what we'll see next time. Okay, convex optimization problems. So an optimization problem is one of the following form. I minimize some function. It's called my criterion. Subject to, that's f of x, subject to a bunch of inequality constraints and equality constraints. So the inequality constraints tell me that gi of x is less than or equal to 0 for a bunch of i's. And the equality constraints tell me that hj of x should be equal to 0 for a bunch of j's. That's just a generic optimization problem. So any optimization problem that you think of can be written in this way. Okay, in D here, I have minimized, and underneath minimized, I have x in D. D is just the common domain of all these functions, f, gi, and hj. Okay, so it's the points for which all these functions are defined and finite. That's an optimization problem. What's a convex optimization problem? A convex optimization problem is one in which this function f, which we call the criterion, and all these functions gi, which are the inequality constraint functions, are convex. They must be convex functions. And moreover, these hj's must be affine. Okay, they must be of the following form. Each hj of x must just be equal to aj transpose x plus bj for a vector aj and for a scalar bj. So we call an affine function. Okay, it's the distinction between affine and linear is I sometimes will say both. Okay, but affine usually is meant to mean that there's some offset. That's a linear function. That's an affine function. But I may mix it up a bit. Okay, but those are the restrictions we place on a problem in order for it to be convex. Convex criterion, convex inequality constraints, and then linear equality constraints. Yeah.
Does it require the domain to be convex?
Well, so what do we know about convex functions? Convex functions have to have convex domains, right? So by definition, so first of all, the domain of H is actually all of Rn, because they're linear. Gi and F, all those must have convex domains. So it's an intersection of convex sets, which we'll see next time is convex. It's a good question. Wow, I really paced it so that we're going to finish on time. So I'm sorry for all the times I said we would quit early. I guess I like to talk too much. So, okay, so this is the very important property of convex optimization problems. It's the first thing we're going to prove in this class. Probably the most useful thing we're going to prove too. And go home and brag to all your friends. This is a very important property. So for convex optimization problems, local minima are global minima. So there is no such thing as an isolated local minimum, which means that if you ever get to a point in your optimization problem in which it kind of looks like you're optimal with respect to every direction you can look, you are at the global solution. That is true of a convex problem. So let's make it a little more formal. A local minimum is a point that satisfies the following properties. Let's call it x. It's in D, so it's in the common domain of all the functions. Okay, that has to be the case. Otherwise, we couldn't even talk about what f of x meant. It satisfies all the constraints. So when a point satisfies all these constraints, we say that it's feasible for the problem. So it means that x satisfies these constraints. Gi of x is less than or equal to 0 for all I, and hj of x is equal to 0 for all j. And if I look at all y's in some neighborhood of x, so if I take a ball at x of radius rho, and I look at all y's that are in that ball, that's what this is saying. The two-norm difference between x minus y is less than or equal to rho. And I look at all feasible points, all points that also satisfy all the constraints, right? G of y is less than or equal to 0, and h of j is equal to 0 for all I and j. Then my criterion at x is less than or equal to my criterion at y. That's what local optimality means. Of course, global optimality means this property is true when rho is infinity. It's true if I compare to any y. But here I'm saying it's just true if I compare to y that are close to my point x. Okay, this is what locally optimal means. So for non-convex problems, you could have a proper local minimum. For convex problems, you can't, in the sense that anytime you have a local minimum, it is a global minimum. So f of x, this property implies that f of x is less than or equal to f of y for all feasible y. So let's prove that, or at least let's sketch the proof. I think we can do it in 5 minutes. Okay, so let's do it by contradiction. So let's suppose that there exists a point z that's feasible. So z must be in the domain, must be feasible. Common domain must be feasible such that f of z is strictly equal to strictly less than f of x. That would mean that actually it's not globally optimal because I could find some other point, strictly smaller criterion value. Of course, what do we know about z? We know that actually z minus x in the two norm must be larger than rho, because I just told you that x was locally optimal, right? So this couldn't be less than or equal to rho. That would violate our assumption. Okay, now let's look at points. Let's call it tx plus 1 minus t times z for t between 0 and 1. Okay, let's call this point y. And we're not going to specify what t is. We're going to let t just kind of be arbitrary at this point between 0 and 1. So let's first establish a few things. What do I know about y being in the domain? Is y in the common domain? It is, actually, because we kind of didn't formally establish this, but this will be clear from next time. The domain is an intersection of convex sets. That much we know already. But the intersection of convex sets is convex. We'll establish that next time. Okay, which means I have a point that's in D, that's Z, and a point that's in D, that's X. So of course, this must also lie in D. That's because D is convex, right? How about, is Y feasible? What do you guys think? It is actually also feasible. So we could check them individually, but Gi of y, which is tx plus 1 minus t times z, because gi is a convex function, that thing is less than or equal to t times gi of x plus 1 minus t times gi of z. Right? But each of these is non-positive. This is less than or equal to 0. That's less than or equal to 0. These guys are both bigger than or equal to 0. Right? It's just t and 1 minus t. T is between 0 and 1. So this whole thing is less than or equal to 0. And you can also, I'll let you check, but because h is affine, we actually get equality there. Okay? So it is feasible. Meets all the constraints. Which means that we can now start talking about what is the value of f at y, because y is actually feasible and it's in the domain. And I'm going to say that for some t, this is the part I'll just make a bit hand wavy, but you can check this. For some t, and t has to be large enough, so close to 1. It's not hard to check. I actually have y being within rho of x. Okay, so the picture is like this. This is x. This is the ball of radius rho. Z is somewhere outside. And all I'm saying is that I can take some point in the line segment that's actually in that ball. That's definitely true. Okay, the ball is positive radius. I just need to take t close enough to 1 in order for that to happen. Okay, so now I actually have a point inside the ball that's feasible. It's in the domain, and it's a combination. It lies in the line segment joining x and z. What do I know about actually f of y? F is convex, right? Another thing about convex problems. So we're going to use the property of convexity for f. It's less than or equal to t times f of x plus 1 minus t times f of z. Okay. What I know is that actually f of z is strictly less than f of x. That was what we assumed, right, up here. X was not globally optimal because z was better than it with respect to the criterion. And actually, close to 1, I should make an important point here. T is actually strictly less than 1. We can actually choose some t strictly less than 1 for which y lies in the ball. So t is strictly less than 1. That means actually this whole thing is actually strictly less than f of x. Okay, because that guy is strictly less than f of x. It's being multiplied by something positive, and this is obviously, f of x times t. So that's it. Now we've come to our contradiction, because we found a point that's inside the ball, y, that's strictly less than f of x, but that violates the locally optimal assumption. Okay, so that was a close to 5-minute proof. All right, we're maybe a minute over, so sorry about that, and we'll see you guys on Wednesday. Don't worry about taking the quiz today. There won't be any quiz, so we'll just discuss that on Wednesday.